Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation, I guess, of these topical MCQs. This is on topic 3, structure and bonding. But what is different is that these are section B type of questions. You can consider them as the following options. So where 1, 2 and 3 are correct, that's option A. Where 1 and 2 only are correct, that's option B. 2 and 3 are correct, is option C, and only 1 is correct, is option D. So these are quite common questions in the Cambridge International A-Level paper 1, but they're also quite common these days across IB and pre-university and all other UK A-Levels as well, because it allows the examiner to test not only one concept but multiple concepts in just one question. You'll be able to tell whether a student really understands the whole thing or not. Okay, so this question is asking you in terms of increasing bond angle. So it's to do with valence, shell, electron, pair, repulsion theory. You'll be surprised at how many students doesn't even know about this acronym, stand for valence, shell, electron, pair, repulsion theory. You have to count the electron pair, the bond pair, and the lone pair. Okay, so these are all happen to be your case study. If I just start with number 2, so water is very happily with 2 bond pair and 2 lone pair, because oxygen is group 16 element. It uses 1 and 2 for forming normal covalent bond. You still have 4 more electrons which are not used for bonding, and this gives you 2 lone pair. So the number of bond pair is 2, the number of lone pair is also 2, 1 and 2 sigma bond, so there's 2 bond pair, 1 and 2 lone pair there. Okay, so 2 bond pair and 2 lone pair, we say that lone pair repel more than lone pair bond pair, which repels more than bond pair bond pair. That is all part of valence shell electron pair repulsion theory, and therefore you have to state all of these after that in order to score in theory paper if you want to talk about the shape and the bond angle. Okay, so therefore it is a band, or some books or some teachers who have called this V-shape. Sorry, not V-shape. Oh, what am I talking about? Not V-shape, they call it non-linear. But I personally prefer band. This is the 104, or you can call it 104.5 degree. That is there, the bond angle there, 104 or 104.5. And then you have SF6, which is octahedral. I'm just drawing the 3-dimensional shape correctly. So that is, each of them is 90 degree, and because you have 6 bond pair and 0 lone pair, so the 6 bond pair repel equally. Okay, this gives the shape of octahedral, which is 90 degree. And again, the explanations matter in terms of stating that and explaining that as part of your VSEPR theory. BF3 is your classic trigonal planar, 120 degree, and these are all part of your AS case study as stated in the specification and syllabus. Yeah, so these 3 bond pair repel equally. You get trigonal planar geometry, which is 120 degree. Okay, so they want an increasing bond angle from this to this to this. This is 104 to 90, that is decrease and then increase again. Number 2 is wrong. Okay, therefore only 1 is correct, because if number 2 is wrong, there's a reason why we check number 2 first. If number 2 is wrong, there can only be one answer. Okay, if I go back to H2O, there's 104 degree. NH3, I haven't talked about NH3 yet, and CH4, but they are again part of your case study, drawing 3-dimensional. So this bolded wedge is pointing at you right in the eye, is coming out from the screen, from the paper. This is going away from you into the screen, into the paper. This is flat. It's the same plane as the screen and the paper. Okay, so it's got a lone pair there because nitrogen is in group 15. So it's used 1, 2, and 3 for bonding. It's still got another 2 electrons there. Okay, so there will be 3 bond pair and 1 lone pair. You have the bond pair and lone pair, which repel more than bond pair and bond pair. Some students, they go and use this thing, but that is for when you have more than 1 lone pair, whereas here you only have 1 lone pair. So how can you be talking about something which you don't even have? Because they just memorize the thing from scratch. They are not even applying to the actual situation. Because you don't have the lone pair repulsion, your bond angle is not as small as this because they don't repel that much. So it's bigger than this, but it's still smaller than tetrahedral, which is the CH4. So your classic organic chemistry, carbon forming 4 bond, that is your carbon sp3 hybrid, that is 4 bond pair, 0 lone pair. So the 4 bond pair repel equally, giving you tetrahedral carbon sp3 hybridization. If you're unsure of this hybridization concept, you can watch my topical playlist on structure and bonding under the hybridization video. Okay, so these are part of the case study. So there's 109 degree there. So ideally speaking, you don't really, it's all about stating, because by this stage, if you are doing this MCQ, you should have a good sound theory of your basic knowledge already, yeah? Especially these are your case study. So CO2 is just, I haven't shown you CO2 yet. I better just get on with that. CO2 is that, you have seen it from O level, carbon form 4 covalent bond. Carbon use all 4 of its outer shell electron for bonding. There's no lone pair. You count only sigma. When you count bonding pair, you only count the sigma. So there's 2 bonding pair because there's 1 sigma bond, there's another sigma bond. When you have a double bond, you have 1 sigma and 1 pi, 1 sigma and 1 pi altogether. You have 1 sigma there and 1 sigma there. So 2 sigma around the carbon, but 0 lone pair. 2 bond pair repel equally. So this is explaining VSEPI. Yeah? Linear shape, 180 degree. Some people, well, when I say some people, I mean students who are weak, they just memorize all of these, but they don't even talk about the repulsion. Whereas the main theory that enables you to determine bond angle and shape and geometry, valence shell electron pair repulsion. Count it, state it, counting electrons, state it, talk about repulsion, okay? So I mean, this question is actually fairly short because we already worked out number 2 is wrong. And this, as you can see, this one increase and then decrease again, so it's not increasing. Okay, so obviously 1 is just the correct answer. My point with this tutorial, however, is not just to give you the answer, but you know, you have the strategy already, but do you have what it takes to go through every single option? Because these are all required in the syllabus and the specification as well. Okay, whatever A-level or IB or whatever you're doing, yeah? In this next question, it's saying that which of the following are features of the structure of metallic copper. We are talking about giant metallic structure. Okay, so there's the giant metallic lattice structure. So we would have the cation, the copper cation, they are all the same size. You only get the cation as a result of you delocalizing the outer shell electrons. These are actually electrons, they are not anions, because metals are elements. Metals are elements. Cation and anion will give you a compound. So what you have is you have delocalized electrons. In fact, they are valence, or you talk about them being the outermost shell electrons. You do not have ionic bond, you have metallic bond. If number 2 is correct and number 1 is wrong, you only left with C, which is only 2 and 3 are correct. You do have a lattice of ions, a lattice of positive ions in a sea of delocalized valence or outermost shell electron. Okay? In this next question, if we look at number 2 first, it's saying that these compounds have the same number of electrons. When you think about the anions, the anion is F minus, and then you have O2 minus, N3 minus, and carbon 4 minus. You are assuming that they are anionic like that. And of course, all of these will have neon configuration, which is 8 electrons total. And then when you look at Na plus, Mg2 plus, Al3 plus, and Si4 plus, all of these would have neon configuration, which is also 8 electron total. So basically, because all the cations and anions, you see the combination is going to be 8 plus 8, 8 plus 8, 8 plus 8, 8 plus 8. They all have neon configurations, therefore they are very certainly isoelectronic. Okay. Electronegativity difference between the elements increases. Well, let's have a look. We know that fluorine is the most electronegative. Oh, if I write that down properly. So fluorine is the most electronegative element. Okay, so if I have a scale, En, so the non-metals tend to be more electronegative than the metals, which would be more electropositive towards that region. Okay, so if I have fluorine there, then oxygen will be there, nitrogen will be there, carbon will be there. In terms of the metals, okay, so which one is easier to lose the electrons? Okay, that means it's more electropositive. It's actually easier for sodium. And we also know that across the period, sodium, magnesium, aluminium, and silicon. And then going that way, En would decrease. It becomes more electropositive. That means electronegativity decrease. So these are also second period. These are all third period from your periodic table. N equal to 3, third shell. N equal to 2. So therefore, we can establish this as silicon, aluminium, magnesium, and sodium. So we're looking at electronegativity difference between the element in each of the compound. Sodium fluoride. Hope you can see. I mean, these are representative diagram. Yeah, they are not the actual value, of course. Maybe I can use a different color so you can see better. Okay, so there's NaF. And then if I use blue for the MgO, so see the difference. How big of a difference is that? Is the difference getting bigger or is it getting smaller? Al3N2, is it? No, Aln. Sorry. Aln. And then of course the last one, without even showing it, that is SiC. Hope you can see the electronegativity difference getting smaller and smaller just by relating to the trend that fluorine is the most electronegative. It decreases that way. It decreases down the group as well. Alright? So electronegativity difference increase, that is wrong. That should be decreases that way. Okay? From sodium fluoride to silicon carbide, the electronegativity difference gets smaller. Number 2 is correct. Number 1 is incorrect. You're left with a simple choice, which is C, which is 2 and 3. Okay? Well, the bonding become increasingly covalent. I hope you can see the trend is that going from sodium fluoride to MgO to Aln to SiC, the electronegativity difference gets smaller. When you have big difference in electronegativity, you are more likely to adopt ionic bonding, where one loses electron and one gains electron. When the electron negativity difference gets smaller, it becomes more covalent. It prefers covalent rather than, meaning sharing electrons, rather than transfer of electrons. Okay, as you go from here to here to here and to here. Okay, so indeed it does become increasingly covalent as the electronegativity difference gets smaller from here to there. Okay. So moving on to the next question. So this is sodium lauryl sulfate. I hope you know, just because it's sure like that, it's actually O minus and then Na plus. So this is a real covalent bond, but this is ionic bond between the two. Okay. So what you have is that all of this is what you call non-polar. They are like your hydrocarbon chain. If you know about hydrocarbon, oils, petroleum, they are hydrocarbon. They are non-polar. They do not dissolve in water. They are also what you call hydrophobic because they don't dissolve in water, right? So they are soluble in oil droplet because non-polar interacts with non-polar. Non-polar dissolve non-polar substance because they can interact via van der Waals between each other. So that's correct. part of the structure is polar and is water attracting. Is that part? Yes. Ionic. This bit. Okay. It's actually ion dipole bond. Okay. So 1 is actually correct. All the carbon bond angles are tetrahedral. So these are CH3, these are CH2. Each of that carbon, each of those carbon bonded to, well, basically 4 covalent bond. See the carbon there? H, H, O, and then the carbon. Each carbon in between, there's a H and a H. 1 to the carbon and 1 to the next carbon. This is also a carbon bonded to 3 hydrogen and 1 to the carbon. So all the carbon is sp3, and that means 4 bond pair, 0 lone pair. That is 4 single sigma bond. That is your tetrahedral 109 degree. Okay, so all 3 of them are correct. This is the last question of this 5-question series. So they say which pair of compound contain one which is giant ionic and the other one which is simple molecular. So you got to know your period 3 oxides and your period 3 chlorides. Yeah? They're part of your topic 9 case study. I think like when I teach structure and bonding, I will have introduced this vocabulary, meaning the compound itself and their structure and bonding in topic 3 anyway. Okay. So if I look at number 2, SiO2 is basically something you have done in O-level. Each silicon is bonded to 4 other oxygen, tetrahedral 109 degree. Each oxygen is bonded to 2 silicon with 2 lone pair on the oxygen and 2 bond pairs, just like water. So there's 104 or 104.5 degree. So it's a giant molecular lattice. Okay, it's not giant ionic, it's not simple molecular. I can cross out 2. Okay, and if number 2 is wrong, there can only be one answer. Okay, but I want to introduce to you the structure and bonding here. Yeah? You will deal more of these in topic 9 under general periodicity, but silicon tetrachloride is a simple molecular structure, but this is definitely giant molecular. Okay, whereas you're looking for one giant ionic and one simple molecular. If number 2 is wrong, only number 1 is correct. Okay, and that is true. You have done electrolysis of Al2O3. That is because they are ionic. Electrolysis of Al2O3 from GCSE or O-level. And then you also have done AlCl6 as part of your AS level dative covalent bond. The aluminium usually is Al with 3 Cl, but it's got an empty orbital. So you use a lone pair there to donate both the electrons in the covalent bond, and you do the same thing with the other one. That's why you have a dimer. These are normal covalent bond. This is a dative covalent bond because both the electrons in the covalent bond comes from only one of the atom. Okay, so what you're gonna have is you're gonna have 4 bond pair and 0 lone pair around aluminium. So that is tetrahedral 109 degree. Okay, when you form Al2Cl6, because now you have 1, 2, 3, 4, you have 4 sigma bond. Okay, and 0 lone pair around the aluminium. The 4 bond pair repel equally as part of your valence shell electron pair repulsion theory. Yeah? So that is indeed simple molecular. Okay, and exists as one single molecule, and there's ionic. Of course, you need 2 of that, and you need 3 of that for the charges to be balanced out. Al2O3. Yeah? P4O10 and PCO3 both are simple molecular. I will draw PCO3 for you, but P410 is slightly harder to draw. So that one is just like ammonia, 3 bond pair and 1 lone pair. You can talk about the bond pair, lone pair repel more than bond pair, bond pair. P4O10 is actually much more difficult to draw. So there is a P or P or P or P4O10. So there's O. So P4O10 is each phosphorus is See, I told you it's actually quite hard to draw, right? Okay, unless you know what you're doing, it will be quite hard for you to do this. Each phosphorus is bonded to 1, 2, 3, 4, 5. Okay, so this is a phosphorus plus 5. This is P4O10. When you dissolve P4O10 in water, you will get H3PO4, which is also phosphorus plus 5. But again, that is something that you will learn more in topic 9.1, which is general periodicity. Okay, with that, I will end this 5-question series tutorial. If you enjoy this channel and the videos I provide, please do subscribe to the channel. Spread the words about the channel to your friends, your class group chat, your relative, whoever else you think might benefit from these videos. Okay, thank you for watching.